Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics and Robotics 320, Robot Operating Systems at the University of Michigan. This will be our 8th lecture. So the topic for today is going to be how we can represent what are called axis angle rotations for our rotational joints within robots. So we'll talk about a number of different ways that we can represent these transformations, including what are called quaternions. So this material will be useful for the upcoming assignment 4. But before we get into it, let me go ahead and minimize myself so that we can all see the slides. All right. So to motivate our focus here on axis angle rotations for the rotational joints in our robots, let's take a look at our upcoming assignment 4, where we're going to be implementing a dance routine for our robots that will extend forward kinematics to allow for the rotational and prismatic joints to be articulated. So one example of what you could implement for assignment 4 comes from a former student of this class who implemented a Beat It inspired dance, which is shown here, where they chose to use the Boston Dynamics Atlas robot for their dance routine, and so this is really a pretty cool dance routine that they had implemented, and so the core part of that is that they were able to articulate the joints and have the robot still be configured in a valid configuration. So not only did they have the forward kinematics working, where they could position each part of the robot, but in addition, the joints themselves could actually take on different states over time to allow the robot to perform the dance. And so as you're working on your forward kinematics, one thing that maybe you could think about is what you would like to do for your dance routine. And if you could come up with an even cooler or a sort of more exciting dance routine than what we just saw. So maybe in the upcoming lab, I'll show you my dance routine that I did when I was a student, which was not as cool as the one on the last slide, I will admit. Okay, so as a little bit of a refresher on where we sort of stand within the course. So last lecture, in lecture 7, we looked at forward kinematics. We sort of started on this topic of forward kinematics, where we built up an understanding of how we can represent the transformations between the local coordinate frames within a robot, so for each link and each joint within a robot, with respect to the world coordinate frame, by using homogeneous transformation matrices. And in addition, we then looked at how we could compute and compose these transformations such that we could position every part, including the end effector of our robots, within the world coordinate frame. And so what we're going to look at in this lecture is we're going to now consider the state of the joints within the robot. Because in lecture 7, we assumed that the joints were stationary, that they wouldn't actually articulate, and that their articulations wouldn't necessarily affect the configuration of the robot. And so we want to extend that in this lecture to understand how the rotations and the translation joints can be included within our forward kinematics routine so that our robots can begin to move. And so next lecture, then, what we're going to look at is how we can have reactive control applied with our forward kinematics routines so that we can actually choreograph motion in the form of a dance that our robots will perform. And so let's start by just doing a little bit of a refresher on what we looked at with forward kinematics. So what you'll remember is that we assume that we're given a description of the kinematic structure of our robot, which we say follows this URDF format. So once again, URDF stands for Universal Robot Description Format. And so within this definition of the kinematics, we have the links defined for our robot and also the joints that connect the links. And so we assume that each of these joints has some axis defined that specifies how that joint will affect the links that it's attached to. So if it's a revolute joint, it might rotate between the parent link and the child link. And if it's a translational joint, it could lead to prismatic action and translations between the parent and child joint. And so anytime we think about these axes of articulation, one thing that we can remember is that this is really a degree of freedom that our robot has within its configuration space. Each joint is a separate degree of freedom. And so in the physical robots, these degrees of freedom are going to be actuated by a physical motor. So for example, we might have a brushed DC motor, which is illustrated on this slide, in order to implement our revolute joints So when the motor spins, it would cause a corresponding rotation in the joint. But in addition, these motors can also be used to implement the prismatic joints that we see in our robots. So on the right hand side is an illustration of how prismatic action can be implemented using these rotational motors by attaching essentially a screw to the motor, which then can lead to prismatic action, which is shown as the up and down motion of the attached links. And so this is a computer science course. So we focus on the modeling of these physical systems, but it is important to remember that within our robots, these motors and the parts that are associated with the robot are physical systems. And so if you're looking to go into more detail about the control of these physical actuators, there are mechanical engineering and electrical engineering courses that are offered within the department. But at a high level, so for our purposes, it's important to remember that essentially these motors are implementing physical systems, and they're using physical phenomenon in order to actuate the control commands that we send from our robot operating system. And so in the case of electric motors, there's essentially opposing polarity magnets that create an electric field, and then based on the current that we pass to these magnets, we can cause the motor to spin in a controlled fashion. And so if you in addition to the brushed DC motor that we looked at, there's also brushless DC motors. And so if you're interested in the distinction between these or going into more detail, so there's one link on this slide, which is an external resource. But like I said, feel free to reach out to us on the course staff, and we can refer you to other courses here that go into the details of the physical actuation. So keeping in mind that we have these physical motors within our robots, for our purposes, we want to understand how it is we can model the joint movement that's going to be actuated by these motors within our matrix stack that we looked at for forward kinematics. So that as these joints get articulated by the motors, our robot operating system is able to understand and is able to configure our robot correctly within the space of the world coordinate frame. So to better understand where articulation is going to fit within our forward kinematics routines, let's go back and take a look at the example for matrix stack recursion that we had looked at in the last lecture. But this time, let's consider that the joints themselves can be articulated, whether by a prismatic joint or a revolute joint. So you'll recall that the input to our matrix stack recursion is going to be a kinematic definition for our robotic structure. So on the left-hand side of this slide, we have an example kinematic structure defined. And so the goal for our matrix stack recursion is going to be to calculate the transformations between each part on the robot, so each link in each joint, with respect to the world coordinate frame. And so the way that this is going to work is we're going to recurse down the tree, building up these transformations one at a time. So to begin our recursion, right, so we start at the root of this kinematic tree, which is in the world coordinate frame. And so, of course, to transform from the world coordinate frame to the world coordinate frame, there is no transformation needed. So the top of our matrix stack begins as this identity matrix, and then we begin recursing down the tree. So the first node in the tree is representing the base frame of the robot, or we could think about this as being the origin of our robot. And so to calculate the transformation from the origin of our robot to the world coordinate frame, what we're going to do is we're going to compose the rotation and translation that transforms from the link 1 coordinate frame to the world coordinate frame. So composing those two transformations together and multiplying them by the top of our matrix stack, which was the identity matrix, results in a new in the new matrix at the top of our stack, which is shown here. And so this matrix represents the transformation from the base frame of the robot with respect to the world frame of the environment. And so using this transformation matrix, we could then position link 1 and the vertices of link 1's geometry within the world coordinate frame by transforming each of those vertices from their local frame, defined with respect to link 1, into this world coordinate frame. And so at this point then our recursion is going to continue. So we're then going to move down to the first joint in our kinematic structure, and we're going to now consider how it is that we can position this joint in the world. And so to do that, we're going to push our matrix stack by one element, as is shown here, where we're going to add now the composition that represents the rotation of joint 1 with respect to link 1, its parent, and the translation for joint 1 with respect to its parent, which is link 1. And so since we assume that that joint 1 origin overlaps with its child origin, link 2, the notation on the new components at the top of our matrix stack, which is shown here with my cursor, is the rotation here and the translation here, which the sub 2 denotes the child of joint 1 is link 2, and the superscript of 1, shown in both of those, denotes that we're transforming with respect to the parent of this particular node, which is link 1. So composing all of these transformation matrices together then would allow us to represent the pose of joint 1 with respect to the world coordinate frame. And so at that point then, we would know how it is that joint 1 would be positioned. However, let's now consider the case that joint 1 actually represents a prismatic joint. And so at this point, our forward kinematics, if it's going to be able to position the remaining links of this branch correctly, it needs to account for the motion that is basically being exerted by this prismatic joint. And so that's now what we want to consider, right? So in other words, we now need to add a new transformation matrix to the top of our matrix stack in order to properly account for joint 1's motion. So within the Knievel stencil, the way that this a portion of the information that we're going to need in order to properly account for joint 1's motion is the axis of articulation. So in this case, the axis of translation that's going to be exerted by joint 1. And so that's going to be defined in the axis property for this joint. So in the case of prismatic motion, we can essentially consider that to be an additional translation that needs to be accounted for. Because essentially when joint 1 exerts some prismatic action, the remaining portion of the kinematic tree, we could think about it as being translated with respect to joint 1. So in this case, in the case of prismatic joints, what we're going to do is we're going to add now a new translation matrix to our matrix stack and compose it with what we had previously. And so this translation here that's denoted by this matrix D is going to take in a parameter here, q sub 1, to denote essentially how much, right, like to what extent the joint is currently being translated by, where this then u sub 1 is denoting the axis of translation that joint 1 is articulating over. And so once again, so by composing that composite transformation matrix, we will then know how it is that the remaining portions of this particular branch in the kinematic tree can be positioned within the world coordinate frame. So if we recurse down our kinematic tree one level, we arrive at link 2. And so by using this composed transformation matrix that was at the top of our stack with link 2's geometry, we can correctly position it in the world coordinate frame, which is illustrated here. And in this case, we're including the prismatic action that joint 1 is exerting on link 2. So at that point then, we'll have reached the bottom of one of our branches. So because this is a recursive function, we'll then pop back up to link 1, and we'll continue our recursion down the remaining branch of the kinematic tree. So in this case, you can see our matrix stack is going to first take into consideration how joint 2 should be oriented within the world, which is going to be using the rotation between link 3 and link 1's frame, in addition to the translation between link 3 and link 1's frame, because again, we assume that joint 2's origin overlaps with link 3's origin before any articulation is applied. And at that point then, we can position joint 2 within the world frame, which is illustrated here. But now let's consider the case that joint 2 is a revolute joint. And so what we want to now do is consider how we can account for joint 2's motion within our forward kinematics. And so in this case, what we need to be able to do is we need to be able to define a rotation matrix that's going to consider the axis of rotation, which is defined by this u sub 2 for joint 2, and the current state of this particular joint, which is q2, which is representing essentially the amount of rotation about this axis that the joint is currently configured in. And so similar to, just as we saw with the prismatic joint, in our Knievel stencil, we're going to be defining the axis of rotation for our joints in the dot axis property, which will be a vector defining that axis in 3D space. And so now, though, what we have to do is we have to figure out how we can perform this rotation. And unfortunately, it's not quite as simple as the case of translation. Because, in the case of translation, we could just define a translation matrix as we had done in the past using our homogeneous definition for translation. But in the case of rotation, it gets a little bit trickier. So now we're going to look at how it is we might be able to implement this. So the first thought is we could potentially use what we used in the case of orienting our joints and links themselves, which was using Euler angles. And that was before we considered the state of the articulations. So if you recall, within Euler angles, what we do is we consider a rotation as being a composition of individual rotations about each of the three possible axes. So we could consider a composed rotation shown on this slide as being a composition between a rotation about z, and then a rotation about y, and then a rotation about x. And so using Euler angles, you have a number of different choices that you could potentially use for the ordering of these kind of component-wise rotations. And so for this course, for your implementations, when you use Euler angles, always use the x and then the y and then the z property, because this is what we'll be comparing your solutions against when we're grading them. But once again, so to consider the articulation of joints, it turns out that Euler angles will not necessarily work all the time. So there's a few issues and challenges that are unique to Euler angles, which we're gonna look at. So just to consider an example of kind of one of the key properties of Euler angles, let's consider a case where we were going to implement Euler angle rotations using a z, y, z order, which means we're first going to apply a rotation about the z-axis, and then a rotation about the y-axis, and then a final rotation about the z-axis. And so what we'll do on this slide is we'll illustrate this series of rotations where the red vectors that we've drawn here along the x, y, and z axes denote the frame as it's being rotated, because the kind of crucial aspect of Euler angle transformations is that as we apply the rotations, our frame is getting modified. Our coordinate frame is getting modified. And so an initial rotation about the z-axis is not necessarily going to mean the same thing spatially as a sort of down-the-line rotation about that z-axis. So let's look at this to start with, and let's say that we begin by rotating this coordinate frame about the z-axis by alpha degrees. So the axis of rotation, since it's the z-axis, is shown now as the dashed red vector. And the rotation by alpha degrees then is going to result in this transformation that we just saw, right? Following this then, we're going to rotate about the y-axis, which has been modified, right? So now the y-axis, following our initial rotation, is shown in this dotted vector, or this dashed vector, which you'll note now is distinct from the initial y-axis that we had in this blue vector that my mouse is pointing to. And so this is a really crucial aspect of Euler angle transformations, because when we now go to apply a rotation about this modified y-axis, it spatially corresponds to a different transformation than if we were intending to rotate about our initial y-axis. So if we now go and we rotate by beta degrees about the current y-axis, we're now going to have a result that looks like this. And then finally, if we go and we rotate about our final z-axis by gamma degrees, we'll now have our final result, which is shown here. And so this is just an example to illustrate this core property of Euler angles. And so so if you want to work through then this particular example, the corresponding math is shown on this slide, which you can do, you can work through offline. But the key takeaway here is that each of the individual rotations that we're applying in this composed rotation is going to modify the frame of reference each time one of the rotations occurs, right? So we saw 3 rotations within this composition. Each time the resulting frame was modified, and so as a result, the sequence of rotations is crucial. And so this can insert a number of challenges for us computationally if we want to rotate about an arbitrary axis, which is what we're going to want to do when we're trying to consider revolute joints within our forward kinematics routine. So let's look at some of these challenges that rotating about each axis one at a time would cause. So one way that we can think about this idea of rotating about each axis one at a time is if we visualize what's called a gyroscope. So that's shown in these figures here, where the various gimbals within the gyroscope would allow for us to rotate about one particular axis out of the 3 possible axes that we could rotate about. And so with this framework in mind, right, so one of the issues that doing these sequences of rotations can cause, this Euler angle rotation, is what's known as gimbal lock. And so gimbal lock is what occurs when 2 of the axes are rotated into alignment. So in the diagram here, it's the case shown in the lower in the lower right image, where in this case the gimbals, which are represented by the blue and green circles, have become aligned. They've rotated into alignment. And so what this does is it actually reduces what was a 3 degree of freedom system down to a 2 degree of freedom system. And it does this based on the axis order that was chosen for this particular sequence of rotations. So one thing that then you should think about is, from a computational standpoint, why might this gimbal lock be a problem for us when we're trying to represent transformations for the components of our robots? So I'll let you think about this for a second. You can pause the video if you want to take more time. So now I'll go ahead and reveal the answer. So the answer is that when you reduce the degrees of freedom from 3 down to 2, you're actually losing the linear independent axis property of your corresponding transformation matrix, to the point that your transformation matrix will have a singularity and become non-invertible. And so this is a real problem for us when we're trying to operate on these transformation matrices for tasks such as inverse kinematics. And so if you want to consider an example of this, and a good example to work through is shown on this particular slide. So let's say that we're working with Euler angle rotations, and we're going to rotate about the z-axis, the y-axis, and then the x-axis in that order. And consider the case where beta, which is the rotation about the y-axis, so the middle matrix in this rotation transformation, is pi over 2. So pause the video, work through this example, and see what the resulting rotation matrix is. So I'll give you a second. And so now I'll click through so that we can look at this. So the first thing that you'll find is that we have if you plug in this pi over 2, you'll compute the following rotation matrix. And if you work through, what you'll end up finding is that this rotation matrix will cause a real problem if you end up multiplying it by a vector. And so this is a good exercise to work through to try and understand. So we can talk more about this during the interactive session. But this is just one example of where this reduction in the degrees of freedom can crop up. Another example is you can actually illustrate with your own shoulder joint, for example, and the rotation that it can perform. So if you try and move your arms in this particular order that we define on this slide, during the interaction session it's much easier to demonstrate, not over a video recording. So I'll demonstrate this myself, but it's kind of a fun example to see this in your own kinematics. So to avoid these issues that are associated with Euler angles, let's consider how we might be able to model a rotation about an arbitrary axis that doesn't have to be composed in the way that Euler angles do. And so to do this, the first approach that we're going to look at comes from Rodrigues with an axis angle rotation. So in this formulation, what we're going to assume we're given is we're given two vectors, A and B. And so in addition to this, let's assume that vector A has unit length, just like the axes that we're going to be working with for projects 3, 4, 5, and 6 have unit length. So by axes, I mean like the x-axis, the y-axis, the z-axis. They all have unit length. And so our goal in this setup is going to be able to transform the vector B by a rotation about vector A of theta degrees. So we want to be able to perform this rotation transformation. And so the approach of Rodrigues axis angle rotation takes the following form. So the first thing that we can observe is that the vector B can be broken down into two component vectors, which we're going to call B parallel, which is the component of B which is parallel to the vector A. And secondly, we have an orthogonal component, B orthogonal, which is orthogonal to the vector A. And so taking these two components, one thing that we can observe is that if you take the sum of the B parallel and B orthogonal, our resultant vector is actually B. And so this is the first the first kind of representation of B that we're gonna use, which is gonna help our calculation of this rotation transformation. So before we look at how this, breaking this vector down into these two components is gonna help with our rotation, let's first consider how it is we can actually compute the components B parallel and B orthogonal. So in particular, the two questions that are good to think about, so you can pause the video and consider these questions for yourself, is essentially what operator would we need, so what vector operator would we need to compute B parallel? And then secondly, what would the equation be to compute B orthogonal, where the sort of hint is that you would be using the cross product for that B orthogonal term. So feel free to pause the video and think about this, but I'm going to go ahead and show the answers. So the first component, B parallel, can be computed using the dot product. So if you take the vector A and you multiply it by the dot product of A with B, you'll have the projection of B onto A, which aligns with this B parallel vector that we're interested in. And then secondly, to compute B orthogonal, we can take the negative A cross with the cross product of A and B. And so that's sort of a useful exercise to go through to make sure that your understanding of cross product and dot product is sound. But at this point, we know that we can actually compute these two component vectors, B parallel and B orthogonal. And so now the question is, how can we use B parallel and B orthogonal to make our transformation calculations sort of possible and simple? So the first thing that we can think about is the fact that B parallel would not be affected at all by a rotation about the vector A, right? And that it's only the B orthogonal component that would be affected by a rotation around the vector A. And so using this fact then, we can sort of think about if we were to rotate B orthogonal around the vector A by this angle theta, and then essentially recompose the B parallel component with this rotated B orthogonal prime, we would actually arrive at our desired vector of B prime. So that would then be the vector B rotated about the vector A by angle theta. So the next question then is, this is nice, but how can we actually, do we think we can actually rotate the B orthogonal component about vector A in a way that's simpler than just rotating B about the vector A itself, which is what we're ultimately interested in. And so if we look at this from a slightly different perspective, we can realize that actually rotating this B orthogonal component about vector A can be thought of as a rotation in a plane.
So if we express a plane that's spanned by this B orthogonal and A cross B, so on the right-hand side of this slide here, so where my cursor is, so we have this plane that's spanned by B orthogonal and A cross B, and we can then note that that the B orthogonal prime that we're interested in would be a rotation in this plane of B orthogonal by theta degrees. And so this we can then observe can be calculated just from trigonometric properties and geometric properties. And so in particular, so the equations here on this slide are sort of standard application of trigonometric functions to directly calculate the B orthogonal prime. And so this then suggests that we would be able to calculate this this resultant vector B prime that we're interested in based on these two components, B orthogonal prime and B parallel. So so you should pause the video here and see if you can work through the sort of final calculation to ultimately arrive at B prime. So I'll give you a second. You can pause the video and think about it. So once you've thought about it, you should arrive at the equation shown here. So at this point, we think we know how to we know how to transform this vector B about A using a rotation of theta degrees. But one thing that we might want to do is kind of simplify this expression that we've arrived at. And so what we can do is sort of we can follow just substitution and grouping steps to try and simplify this equation slightly, until ultimately what we can realize is that this expression can actually be implemented in matrix form. So the equations here shown on this slide, I'm not going to walk through them in too much detail, but the kind of key takeaway is that we can actually implement this Rodrigues axis angle rotation transformation as a series of matrix vector operations. And so and the benefit once again of this is that we don't necessarily have the issue of Gimbal lock and so forth that we saw with Euler angles. The one maybe downside with this approach is that the resultant transformation matrix shown on this slide is not very kind of friendly, right? Like you can see here it's going to require a pretty large number of individual operations, and there's potential for implementation bugs and so forth because of the complexity within this matrix. And so that motivates maybe this question of whether or not there might be a cleaner expression for this form of axis angle rotation. So the next approach that we're going to look at is going to move us towards this goal of having a kind of cleaner expression for axis angle rotation. And so in particular, this approach is going to be using rotation by complex numbers. So before we look at the case of rotation within 3 dimensions, let's first consider rotation by complex numbers in 2 dimensions. So as a brief refresher, you'll remember that a complex number can be expressed as a real component plus an imaginary component. So in this case, we have a real component A plus this imaginary component B, where the unit of the imaginary numbers, I, is equal to the square root of -1. And so we can visualize this complex number A comma B as existing within what's called the complex plane. So the horizontal axis within the complex plane denotes the real component, the real number line, whereas the imaginary numbers are represented on the vertical axis, where the unit, once again, is I. So if we have a unit vector, right? So let's say we have this unit vector A comma B. We can think about this unit vector as existing within the complex plane according to a rotation of theta degrees about the plane's axis. And so the vector notation of A comma B can be thought of as equivalent to what's known as Euler's formula, which is given here. And so the key thing to notice within Euler's formula is that we're expressing this point according to its rotation within the complex plane. where once again, where this point is a unit vector. So it exists along the unit circle in the plane. And so the property of Euler's formula that we're going to sort of be, that we can kind of observe to make the connection to rotation is then shown in this final bullet. So if we have two complex numbers and we take their product, so if we multiply these two complex numbers together, we can express that in this equation here. So if in vector notation, we can express it in this way. But alternatively, if both of these complex numbers are expressed according to Euler's formula, we can observe that the multiplication of these two numbers is composing the two rotations together, where these two variables in the exponent here are denoting the rotation that was the complex number z, and then separately the rotation that was for the complex number w. And so this is now hinting at how we can use, in a much kind of cleaner mathematical form, multiplication within the complex number space to represent rotations. And so now that we have some intuition for the case of rotations within the 2D complex number space, let's consider how this will extend to the space of 3D rotations. So in particular, this is where we're going to now be using what's known as Quaternions. And so once again, just to reiterate, so the big appeal of Quaternions is that we don't have to consider this axis order that we did when we had Euler angle rotations, because we're performing simply axis angle rotation. And in addition to that, we're going to alleviate the problem of gimbal lock that we saw with Euler angles. And so Quaternions are, you can think of it as performing Rodrigues axis angle rotation, but within 3D space. And it's a nice framework for composing and interpolating between rotations in the space. So while in the 2D complex number plane that we saw on the last slide, there was a unit circle that where points existed on the unit circle, and then we were composing the rotations about that unit circle. For rotation matrices, for rotation transformations in 3 dimensions that use Quaternions, the unit Quaternions are going to exist along the surface of a 4-dimensional unit sphere. And so it does get slightly more complex, at least for me, to conceptually visualize. But you can keep that in mind, that we're sort of taking that idea that we saw on the last slide and extending it to now a unit sphere in 4-dimensional space. And so if you're curious about the origin of Quaternions, these go back to Sir Hamilton, where he actually had this idea, or what's described here, this flash of genius, and actually, I believe, carved the idea into a tree at the location that he sort of had this idea. So it's an interesting story that you can read about if you're interested. But if we look at sort of the details of this representation, so for Quaternions in 3 dimensions, there's going to be 3 separate imaginary components and 1 real component. So the imaginary components will be denoted by the terms I, j, and k, that collectively provide a basis with the following properties. So in particular, each of these imaginary numbers has that property that they are the square root of -1. Right, so I squared is equal to -1, j squared is equal to -1, and k squared is equal to -1. But it's important to note that I does not equal j, and j does not equal I, and j does not equal k, and k does not equal j, and so forth. So these are different. You can think about these as being not equal terms, but they are all equal to the square root of -1. And in addition, they satisfy the remaining properties then that are shown in the following 2 bullets. So these imaginary numbers are related according to these equations shown here. So ij is equal to k, jk is equal to I, and so forth. And so one of the observations we can take from these properties is that they form a 3D basis based on the observing some properties that where they're related through their cross products. And so ultimately, like I said, so having a single quaternion is going to be defined as 1 real component combined with one of each of these imaginary components, where these terms A, B, C, and D are scalar values, are scalar values. And so we can represent then a quaternion as a vector. So we could call quaternion Q as being equal to a vector that is A, B, C, and D, where there's this one real component, and then we have an imaginary vector component. So given this, so a few additional points that it's important to mention about quaternions. So quaternions live within a vector space, and so we talked about vector spaces within our linear algebra lecture. So vector spaces are closed under both addition and scalar multiplication. So as a result of that, if we have two quaternions and we add them, the result will be a quaternion. And if we take a quaternion and we multiply it with a scalar, the result will also be a quaternion. In addition, then, the multiplication formula for quaternions is shown on this slide here. So I won't walk through it, but one key detail to point out is that quaternion multiplication is not commutative. And so multiplying, so the order does matter when you perform multiplication. In addition, so a few other properties that are useful to note, and some equations that will be useful when we begin implementing quaternions for project 4 are shown on this slide. So we can take the norm of a quaternion by taking the sum of squares of its components. We can take what's called the conjugate quaternion by negating the imaginary components of the quaternion. We can take an inverse quaternion as shown here. So we take the conjugate and divide by the norm squared. We can then define a unit quaternion as any quaternion with length 1. And so as a result of this definition, we can observe that the inverse of a unit quaternion is simply the conjugate quaternion. And so using these properties of quaternions, we can then define how it is that rotation is actually implemented by a quaternion. And so in particular, rotations are going to be represented by unit quaternions, which you'll recall from a few slides ago. Each unit quaternion can be thought of as a point lying on the 4-dimensional unit sphere. And so if we have given to us some axis and some angle that we want to rotate about that axis, we can express that axis angle rotation using a quaternion that's defined here. So what we'll have is for the real component, we'll have cosine of theta over 2, where theta is that angle that we want to rotate. And then for our imaginary vector, we would have the x component of our axis of rotation multiplied by sine of theta over 2, our y component of the axis of rotation multiplied by sine of theta over 2, and then finally we'll take the z component of our axis and multiply it by sine of theta over 2. And so collectively then these 4 terms become the one real term and then the 3 imaginary terms within our unit quaternion. And so once we have this quaternion, if we want to rotate some point in 3D space, which we'll call P, by this quaternion, right? So if we want to perform this axis angle rotation, for example, on the vertex of a link geometry, we'll be able to implement that rotation using the process that's defined on these final 4 bullet points. So in particular, what we'll first do is we'll express the point P itself as a quaternion, which we're going to call V. And so this quaternion V is going to be constructed with that's as defined here. So we'll have no real component, and then it'll have simply the x, the y, and the z coordinates expressed as the imaginary vector. And at that point, then we would perform 2 kind of consecutive quaternion multiplications. So we would multiply our quaternion for the axis angle rotation Q by V, and then also multiply that by the inverse of the quaternion Q. And so at that point, then we would have our rotated point P, which we could extract from the result V prime simply by taking the imaginary vector to be the coordinates in 3D space. And so with that, here's a checkpoint that we can that you can use to make sure that you're following so far our math for quaternions. So I recommend you pause the video here and try and see if you can answer these questions yourself. And what we'll do now is I'll start to walk through them. So the first question here is, what would be the unit quaternion for axis angle rotation involving no rotation? So in this case, it would be the identity quaternion, which is following from the fact that cosine component will be 1, and the remaining sine components with no rotation would be 0. Next, if we ask what would rotation of 80 degrees be about the z-axis, if you work through that, you'll find the following quaternion. And similarly for the remaining 2 examples here, if you work through those, you should arrive at these answers based on those trigonometric functions with these specific angles. So just to restate, so quaternions. So if we have 2 quaternions, so q and negative q, these will give the same rotation. Composition of rotations can be implemented as multiplying the quaternions. And it's important to remember that quaternion multiplication does not commute. So 3D rotations do not commute. In other words, the order in which you apply these quaternions matters. And so once again, another thing to restate here is that Rodrigues and quaternion axis angle rotations are equivalent. And so this slide works through the actual proof of that, where we show how essentially multiplying in the quaternion form will ultimately result in the same Rodrigues axis angle rotation equation that we saw earlier. In addition, what we can do is which is how we're going to be using quaternions for assignment 4, for example, is we can express quaternions in a rotation matrix form. And so in particular, we can have either an inhomogeneous 3D rotation matrix based on a quaternion, which is shown in this first bullet, or we could equivalently express a quaternion as a homogeneous matrix, which is really what we're going to be focusing on for our projects. And so rotation matrix, and also we can also go the other way. So we can also take a rotation matrix and compute what the corresponding quaternion would be. So in our case, right? So what we're going to do is we're going to have a quaternion formed from the axis of a particular revolute joint and the corresponding motor angle that joint takes at a particular time. So based on that axis and that angle, we'll be able to first form our quaternion Q using the formula that we have here on this slide. And then using that quaternion, we'll then be able to form our rotation matrix, which then we can apply within our forward kinematics matrix stack. So if we go back to our matrix stack and we think about where this fits in, so if you remember towards the start of this lecture, we were at this point in our forward kinematics recursion where we were arrived at joint 2, and joint 2 was a revolute joint that had an axis defined, and it also has correspondingly a current motor angle as part of its state. And so what we'll do is we'll formulate this rotation matrix here based on the quaternion math that we saw on the previous slide. And so using that quaternion to rotation matrix conversion, we'll be able to define this rotation matrix, which we couldn't at the start of this lecture. And at that point, then we'll be able to correctly position link 3 according to that rotation, and we could continue on with further joints down within the remaining portion of the kinematic tree. So at this point now, we now have the ability to represent the current state of all joints within our forward kinematics and model the articulation that's induced by that current state of the joints. And so what we can do is we can kind of put a check there, right? So now from the previous lecture, we know how to implement the forward kinematics as a matrix stack recursion, and now we've added on to that the ability to express these articulated joints within the forward kinematics process. And so in the next lecture, what we're going to be looking at is how we can apply some reactive control that's integrated with our forward kinematics, so that ultimately our robots will be able to begin performing actions. And so for assignment 4, these actions that we're going to want our robots to take is a choreographed dance routine. So a few other thoughts that we should think about now that we're considering forward kinematics with these articulated joints. The first is when we think about physical robots, such as the fetch robot shown here. There's one question which we haven't really addressed yet, which is this idea of joint limits, right? So of course, on a physical robot system, on most physical robot systems, certainly the fetch, each joint will have some physical limit beyond which it either cannot rotate due to the intrinsic property of the joint itself, or potentially, which is something that we'll look at further on down in the remainder of this course, if there's potential collisions with the environment. But internal collisions, so limits on the joints themselves, also have to be modeled within forward kinematics. And so, in particular, the way that this gets expressed is actually within the URDF kinematic description of a robot. So here, for example, are two of the joint descriptions taken from the fetch robot. So we're looking at first of all, a prismatic link, which is the torso, which can vertically raise up and down. So here you can see we have a limit defined as part of the URDF for that joint. And similarly, for one of the shoulder joints, we have which is a revolute joint. It also can have a limit defined, which defines essentially a lower limit and an upper limit, beyond which the joint cannot rotate. So those are highlighted here. So in our course, we also have the ability to consider joint limits for the robots. So for example, for the fetch robot or the PR2 robot model, we express the joint limits as being property of a particular joint within our JavaScript version of URDF. So if you choose to, the implementing forward kinematics for these physical robot models is optional for this course. But if you do choose to implement the forward kinematics to work with the fetch and the PR2, I suggest that you consider these joint limits and incorporate them into your forward kinematics to ensure that you don't apply transforms that would exceed these limits. All right, so a few other kind of remaining notes then that are important to point out as we move towards Project 4. So the first is just want to reemphasize that you should be using the order whenever you use Euler angles within the forward kinematics routine, which would be used for positioning the links in the joints. You should always use the X, Y, Z order of performing those rotations, because this is what the code will be graded based on. In addition, one really important function that is crucial to implement is the vector cross function, which is one of the helpers. And so the reason for that is that this is used for visualization, and it's also used throughout the code for a number of useful functionalities. In addition, so you'll have the ability to actually move the robot's base within the world, but these controls have to be implemented as part of the Knievel stencil. And in addition, then I'll point out that the origin field of links and joints is used to store the transforms without considering the joint motion. And so this is really used just for debugging. Finally, then, one other important thing that we sort of implicitly hinted at, but it's worth pointing out just explicitly, is that in our version of a URDF, a joint and its child link will share the same coordinate frame. And so we saw this when we were stepping through the forward kinematics recursion, but just pointing that out here explicitly so that just to clarify that. So one case of where vector cross is important is for, like I said, so for visualization purposes. So if your vector cross is implemented correctly, what you should, and your forward kinematics as well, what you should see are the joints, which are shown as the cylinders within our visualization here. They should be aligned with the axis of rotation that they apply. Commonly, if you haven't implemented vector cross, or if it's not implemented correctly, you'll be able to notice that very quickly by seeing that the joints do not align with their correct axis of rotation, or prismatic action in the case of prismatic joints. So this is important to think about when you're implementing those functions. In addition, we have built into the Knievel stencil a set of controls for the robot. So we're going to use the WASD controls for moving the base of the robot. And so I'll talk more about this at the upcoming lab and demo what this will look like, but I just want to point that out for those of you starting to look into some of these Knievel stencil files. And so one visualization that can be useful is by displaying the axes for the base joint. So in our case, when you visualize the axis for the base joint, you should note that the blue axis is going to correspond to the forward heading of the robot, whereas the red axis will be the lateral heading, sort of the sideways heading. So as one final brief topic, let's revisit how it is that we define kinematics for our robots, and let's consider a few alternatives that exist. So three common approaches are summarized on this slide. So one approach that you might see references to, for example, the Spong book discusses this at length, and also, for example, in the course Robotics 550, if you go on to take that course, you will see the Denevit-Hartenberg convention. In this particular course, we're using this matrix stack convention, and then in addition, a common approach which you'll probably see references to within literature is the use of dual quaternions to represent kinematics and rigid body transformations. So I just want to highlight these just so that you're aware that the alternatives to forward kinematics do exist. And so if you're interested in exploring some of these, we can discuss more during the interactive session. Our particular choice of using the matrix stack in this course is motivated because the matrix stack has nice intuitive properties for understanding what these individual transformations represent and how we compose them. And in addition, for implementing, it provides a nice framework that we can embed nicely with our robot operating system. And so with that, let's now foreshadow what we're going to be looking at in the next lecture, which is going to be finite state machines. And so in particular, what we're going to be working towards is allowing our robots within our Knievel stencil to be reactive and make decisions and take actions by using these finite state machines to transition the configuration or the state of the robot over time. And so with that will conclude today's lecture, and I look forward to seeing you this week.